For these notes, we're going to talk about the heat of fusion and heat of vaporization. It's kind of similar to specific heat, but a little bit different. So when a phase change occurs, so for example, liquid freezing or a solid melting, it requires energy, or energy is exchanged. So it requires energy to melt a liquid, and when a liquid freezes, it releases energy. It's really similar to a specific heat in that each substance has releases or gains a certain amount of heat during a phase change. The only difference is that at that point, the temperature doesn't change. So specific heat is more about the motion of the particles and like making them move faster or slower by like the change in temperature based on how much energy it takes to make them move faster or slower. Heat of fusion is more about breaking the intermolecular forces or electrostatic interactions to actually make that phase change happen. And that phase change, again, there's no temperature change. It's just the position or the state of the atoms. So for example, if you have ice, all of the water molecules are locked in like a rigid kind of hexagonal sort of pattern. Breaking those bonds or those interactions requires energy, and that's what melting is. And that's what allows the water molecules to then start moving freely. So at 0 degrees Celsius, at water's melting point, water can exist both as a solid and a liquid simultaneously without there being any like temperature change. So the actual motion of the particles, the speed of them, the kinetic energy doesn't change. Basically what you need to know about this, it's the energy released when liquid freezes or energy needed to melt it with no temperature change. And there's a formula, and the formula is Q equals M delta HF. So let's parse what that means. Q, we already learned from specific heat means energy or heat in joules. M is mass in grams, very, very straightforward. Now, this time we have delta HF. Delta HF is the heat of fusion or enthalpy of fusion. We will learn way more about this in AP chemistry. But enthalpy, yeah, it's kind of like the internal heat or energy that is stored within the interactions of molecules. It's measured in joules per gram. Sometimes it's also measured in joules per mole. That's another way of measuring it, but we're going to use gram. And the delta stands for change, the H stands for heat or enthalpy, and the F stands for fusion. The delta in this case is not something you have to worry about. The delta H is always something that you're going to be given. It is very much like the specific heat, the C, in that it's just a number that is given to you. And that's very specific to a specific substance. So each substance has its own heat of fusion. So let's check out a couple of sample problems and we'll see how this goes. So the heat of fusion for water is 334 grams joules per gram. So I'm going to underline that. That seems important. How much energy, okay, that seems like Q to me in joules, is required to melt 50 grams of ice into liquid water? Okay, so same as always, we've got our formula here and we're just going to go ahead and use it. So Q is equal to M and the heat of formation times the heat of formation. We have the mass, we have the heat of formation, so we just got to plug it in. And you know, I just realized I left my calculator over there, but I've got I'll choose my phone because it's right on hand. So 50 times 334, that is equal to, oh, it's a big number, 16,700 joules, because the grams cancel out. And that's how much energy it takes to melt ice. No temperature change. We don't have to worry about temperature at all. And that's pretty much it. I will make another note that you can convert this into kilojoules if you want. Just divide it by 1,000, because that's a little bit nicer. It's a little smaller number. 16.7 kilojoules is a little bit more reasonable, but they're the same thing. Okay, so that's pretty much how you do it. It's another formula. You just plug in all the necessary numbers. Let's take a look at another example. if it takes 41,000 joules of heat to melt 200 grams of solid copper to liquid copper, what is the heat of fusion of copper? So this time it looks like we are solving for heat of fusion. So we'll start off with our equation. And we're trying to solve for delta, the heat of fusion, that one. That's one variable. I know it has like 3 parts to it, but it's really just one variable. So we're going to divide both sides by mass. So we're going to get the heat of fusion. Again, it's a weird variable, but just go with it, is Q divided by M. We've got our heat is the 4100 joules and 200 grams. So it looks like our answer is going to be 41123 divided by 200 equals 205 joules per gram. And that's our answer. So it looks like it actually takes less, the heat of fusion for copper is less than for water. Isn't that kind of interesting? Now the actual melting point of copper, of course, is a much, much higher point. So it takes a lot more energy to even get copper to the right temperature, but there you go. Okay, let's talk about heat of vaporization. Heat of vaporization is the exact same concept, except this time it's for gas to liquid. So this one was between, this is if you're going in between solid and liquid. This one is going between gas and liquid. I do the capital L's just so that you can, or the cursive L, so you know that what that means. Handwriting can be a little tricky sometimes, so I'm trying. So yeah, it's the exact same thing. Again, no temperature change. So you can have water at 100 degrees Celsius, which is its boiling point, and it will be liquid water, but it can also be steam. It can also be a gas. And it kind of goes in between those two. So we have the exact same formula, you'll notice, except instead of an F, it's a V for vaporization. Actually, when you get to AP Chem, you'll see that there's tons of heats of delta H's for all different kinds of things. All different kinds of reactions. There's one for sublimation, there's one for crystallization, there's one for dissolution, dissolving something, all kinds of cool stuff. So let's dive right in. So the heat, same idea here again. We've got our Q is for energy or joules, M is for mass, delta HV is one variable, even though it's weird, and it just stands for heat of vaporization. Once again, joules per gram. Sometimes you might see it as joules per mole, but that's more of the AP. We'll do that more in AP. Okay, so the heat of vaporization for water is 2,500 or 2,257 joules per gram. What is the energy in joules? Ooh, it tells us the unit. That's nice. Required to convert 50 grams of water into steam. Now, it doesn't say this here, but this is going to be at 100 degrees Celsius. And this one was at 0 degrees Celsius. That's kind of important. It's at its boiling point or at its melting point. Okay, so let's go ahead and do this. Hold on, I'll make a little dividing mark here just to keep everything separate. Okay, so we are trying to solve for joules. That's energy, so that's going to be Q M delta V. So we just have to put in 50 grams times 2,257 joules per gram. Grams cancel. We're left with joules. Once again, let's do a little bit of math here. It's going to be a pretty big number. You'll notice that the heat of vaporization for water is quite a lot bigger than the heat of fusion. Think of fusion like fusing something. It's like, you know, going from a liquid to a solid. And that kind of makes sense because you have to break a lot more of like the hydrogen bonds or like the interactions between water and you're adding a lot of space to go from a liquid to a gas. So it makes sense. It requires a lot of energy, which is also why melting water is not very difficult, but boiling it takes a lot more energy. Okay, it looks like our answer is 112,850 joules, which you can also write as 112.85 kilojoules. Either one doesn't actually matter. Okay, So very similar kind of problem solving. Let's take a look at another one. The liquid sulfur vaporizes at 445 degrees Celsius. If it takes oh God, that's a big number, to convert 20 grams of liquid sulfur to at 445 degrees Celsius to gaseous sulfur at 445 degrees Celsius, what is the heat of vaporization? So we have these temperatures here. Sorry, heat of vaporization is what we're solving for. And that's just telling us that this is all at the boiling point of sulfur. So the temperature doesn't actually matter in this case. It's just reminding us like, hey, we've got this liquid sulfur, it's at the boiling point. We're converting it to the gas at the boiling point. We're not raising the temperature or lowering it, staying the same. So that means we are allowed to use this formula because there is no temperature change. If there were a temperature change, it's a little more complicated, which we're going to get into in the next video. So, oh no, my lights went out. That's okay. We'll use this for right now. Okay, so we need to solve for heat of vaporization. So we get Q equals M H V. We're solving for that. So let's divide each side by mass. So delta HV is equal to Q divided by mass, which is going to be 28125 joules divided by 20 grams. Ooh, that's a big number. And that is going to, oh, I did that in a weird way. That's okay. I'll put the answer up here. It's fine. And let me get the lights on while I'm calculating this. Ooh, I'll grab my calculator. Oh, there we go. So, okay, lights off. Just grabbing the calculator. I like it better. 8,125. 28. Nope. Nope. Not that. Delete. 28125. You got to double check your work all the time, otherwise, you know. All right. So it looks like we have the answer is 1,406.25 joules per gram. We can also write that as, if we wanted, 1.0401 like kilojoules per gram if we wanted, but we don't have to. So same basic idea. Okay, so let's take a look at your unit packets. You can see the work that's related to this, the practice problems. This is going to be page 14 and 15. And I think I picked out 2 problems to check out. So these are kind of all mixed up together. So you do kind of have to pay attention a little bit. Okay, there is a lot of information in this paragraph that we might end up needing. So we'll have to do this. I see this number comes up a lot, and I also see this one. So we might need one of these numbers, any one of those. So it's 2 numbers that keep coming up a lot. So we'll figure out which ones we need. The latent heat of vaporization of water is, oh, it's right here. Same one as here, that's perfect. 2,260 joules per gram. How much energy is released when 100 grams of water condenses from vapor at its boiling point? So that's perfect. Okay, excellent. So we are solving for heat. So that's Q is equal to M delta H, and this is for vaporization. And we just need to plug in the numbers here. So it's another pretty easy one. 100 times 2,260 joules per gram. I'm not even going to need my calculator for this one because we're just multiplying by 100, so that's easy. 2,260 with 2 zeros at the end. Joules, also known as dividing by 1,000, that'd be 226 kilojoules as an answer. Okay, that one's pretty straightforward. Okay, let's try another one. Oh, yep, number 4. The latent heat of fusion of water is 334 joules per gram. How much energy is released when 20 grams of water at 0 degrees undergoes freezing. Oh, okay. This is actually pretty similar. Q equals M delta H of F. We've got our mass is 20 grams times 334 joules per gram. Grams cancel. Yeah, this one's very easy. 334 times 20 is equal to 6,680 joules, or 6.68 kilojoules, whichever you prefer. Okay. Now, let me just take a quick look at this and make sure we're good here. Yeah, these are kind of fun. These ones have the answers in them already, which is very, very nice. Oh, this one, the second page uses calories per gram, but that's okay. You can use calories per gram. I didn't even notice that about this worksheet, but that's okay. Just use these numbers. Joules and calories are very similar to each other. So it's just another way of measuring. It's a non-metric measurement system. So that's not too bad. Yeah. There's also some specific heat in here as well. So that's not bad at all. Now, what we're going to move on to next time is, just to give you a little preview, is these phase diagrams, other phase change diagrams, where if you want to move between two different temperatures, if there's a phase change involved, you kind of have to keep that in mind. So we're going to kind of go into that next time. But for right now, I think that's a great place to stop. And we'll got one more video for the student left, I think. So great.